Good morning, everyone. Just to put context first, why are we here today? And what about designing custom optical instrumentation for the purpose of looking into the brain? Throughout this presentation, I have some code that you can download at this address. Just look up on my website. It's called Open Source Tab. I wrote a little MATLAB code to discuss very simple functions about wave propagation and lens operations. Everything is really well curated. I used it for my class for teaching, so it's not fast computation, but it's really easy to understand, and I encourage you to download it and run it through the talks. I'll show some results. So why are we here today is to build better optical brain-machine interfaces. And the idea is that we would like a device that can read and write into the brain. It's important for our line of work, neuroscience research, to understand how the brain works, what it does. It's interesting for medical research. That's how we get money. We apply for grants and we say we're going to solve brain disease and find better drugs. And more importantly, that's really our dream. We would like to connect the brain to enhanced prosthetic devices and give functionality to devices that can be grafted directly onto the brain. So with that, when you start talking to neuroscientists and you tell them, what exactly do you need to look into the brain, what do you mean by that? They tell you about the brain. They tell you that these neurons are really small, 10 microns, that there are billions of them in the brain, and that they operate by means of action potentials that happen really, really fast on the time scale of a millisecond, and that they would like to be able to read and write in many, many neurons at once at speeds that are really, really scary from the perspective of a computer science person. And then they add, their wishes. They want to be able to do that in 3D, in large 3D volumes. That's because the neural code is distributed. They want single neuron spatial resolution. That is because two neurons that may be next to each other might completely encode different information. They want to be addressing many neurons in parallel. That's because the neural code is involving many neurons at once for any basic function. And with the temporal resolution we've been talking about, and ideally online to perform read and write operations, the conversation, responding to the brain as the activity is ongoing. And ideally biocompatible and miniaturizable, why not? This is the whole list of things to do. And so optical methods are great because you can use optogenetics to label or to put an opsin at the surface of the membrane of the neuron that when it receives light activates the neuron. And you can also use, for instance, calcium or voltage reporters that modulate the fluorescence as a function of a physiological property, for instance, the presence of calcium of the voltage across the membrane. So those tools are there, but the technology is not there. So this is what I do in my lab. We do a bit of optics, computer science, and neuroscience in order to, with a combination of work at this interface, develop technologies that can solve those problems while navigating all the constraints that are brought to us by neuroscientists. So the outline for today is I would like to start with a brief and as evolved as you want introduction of optics. We can spend an hour on that, so I will try to push things forward. Then I'll talk to you about this technique that I developed when I was a postdoc at Berkeley, which is called 3D shot, that allows you to do multi-photon activation of custom neuron ensembles and has been really tailored to try to satisfy all the criteria we just seen before. And then as hologram is at the center, hologram generation is at the center of this purpose, we'll focus on techniques to compute holograms. We'll see how, basic principles of holography. Then we'll talk about ways to make holograms really well with an optimization technique. And then we'll talk about some recent work that's yet unpublished about generating holograms really fast with deep learning methods. And then I'll try to talk to you about what I mean by task-oriented computer-generated holography, which I think is the way to address the problem from the perspective of the world of neuroscience. So to get started, I'll just try to not overlap too much with what Professor Smith has just said, but start with my vision and my perspective on the Huygens-Fresnel principle. So what we're doing is wave optics. We have typically one wavelength at a time. Everything is coherent. And the way I represent it is you have to imagine that you're on the side of a swimming pool. And this is you creating an oscillation wave on the swimming pool. And what you're interested in knowing is at another location here, what would be the oscillation? And what you see is that there is this phase delay here that is related to the distance, the time it takes to go from here to there. When you have multiple sources, because we are in the world of coherent waves, these can be added. So you can add the contribution of one wave, the contribution of another wave, and if you have two sources located on the edge, you can calculate what will be the oscillation over there. Everything happens in steady state. This is the basic principle of Huygens-Fresnel. And the idea is that when you have multiple sources, you apply the Huygens-Fresnel principle. Tells you that to calculate the field anywhere, you basically decompose your field as point sources along a known contour, and by propagating the contributions of each of these treated as point sources, you can calculate the oscillation that you will be able to see here. Now, of course, we're not going to do that manually all the time. You can put that into equation. This is called the Fresnel-Worth propagation equation. And that equation, in simple terms, tells you that if you know the 2D phase and intensity in a given plane, so here in z equals 0, this quantity, you can calculate, and it fully determines the rest of the light distribution in the entire 3D volume via this convolution operation. That's Fresnel-Worth propagation. And there is a demo that implements this equation. And this is, for instance, one of the things you can do. You specify an intensity profile, so a custom image, and you can simulate at a certain distance what the wave that you have in this z equals 0 plane can become at a custom distance. So this is like a function that's all coded. You just apply the parameters of your space. You sample the image with a defined window size. You decide on the wavelength, you decide on the propagation distance, and you can calculate this complex field and, for instance, display the intensity. So this is a basic principle. Another interesting principle of optics is to think about relays of information in optics. So the system I draw most often, I think I draw about one a day these days, is called the 4F system. So you have a lens here, it's perfect, ideally thin lens. Another lens right here, and each lens defines, a focal point here and a focal point there, and we put the two lenses on the same optical axis in a way that the focal points here intersect. So you can trace a bunch of rays, and you can see that as you trace rays from different point sources, if you have an object here, you will get a reverse image right there in the opposite side. So this is how we make optical relays of information. A microscope uses a lens of short focal length here, that's the objective, a lens of long focal length here, that's the tube lens, and we'll make a relay of information from the object that is microscopic under the objective to the detector, which is going to be where the camera is. That's in a perfect world. In practice, Santa does not exist because those systems are imperfect. A simple way to model imperfection is to say that those lenses do not have, no matter how much money you spend in making them extremely wide, do not have the ability to capture all the rays that your sources emit. So you're losing some information. We can model that very simply by representing, for instance, the finite diameter of these objects. And when you compute the transfer of information from here to here with a finite aperture, you generate something which is called a point spread function, which is the image of an infinitely small virtual or hypothetical point source located here onto your detector. And so those devices, for instance, this type of assembly, is also known as a shift invariant device. If you move the point source that is here, you move equally the target image that is here, and the point spread function does not depend to the first order on the location where you're of your point source. What that means is that you can define what is called a point spread function, which is the image of an infinitely small point. And in an optical system, the point spread function becomes a convolutionary tool, which means that if you have an object, so this is, for instance, your density of fluorophores under the objective, if you know the point spread function of your imaging system, the image is a convolved operation of the object, which is the light source, and the point spread function. So that's pretty much all I would say one need to know about optical systems to get started doing really interesting things in the field of optics. Another thing I'd like to put forward is that a lens performs an elliptical Fourier transform. So we can go through the equation very simply. Imagine you have a wave coming here in this plane, defined by the complex field A of x. And you're interested in calculating what the field is in this plane B of x. To calculate the field is very simple. You apply Huygens-Fresnel. You say the field that is here will be the sum of the contributions of each point located on this axis treated like a point source modulated by the phase delay created by the time it takes to go from here to here. Now, you can see that the time it takes to go from this here to any point on the orthogonal set of lines here is the same. So what matters really in this equation is, as a function of x, the extra time dr that you get at any location x compared to the target here. So you can say that b of x prime is the sum from minus infinity to infinity of a of x multiplied by the delay, the effective delay, which is basically this distance dr, e to the I 2 power over lambda dr of x. First approximation, paraxial approximation, you can see that dr over x is about minus x prime over f, saying this angle here is about the same as this angle right here. And if you write down this equation correctly, you end up with this expression that says what b of x prime is as a function of a of x. Map that to the definition of the Fourier transform, and you end up finding that the field that you observe as a function of x prime is the Fourier transform of A taken in k equals x prime over f lambda. So you have built a Fourier transform operator. Great, because now you go back to your math lessons and you say, if I have a forest system, I operate a Fourier transform here, and I operate another Fourier transform right there. You go from real space, your object, to your image via an intermediary Fourier plane. In fact, you will see that your image here is flipped, which is also a property of Fourier transforms. More importantly, now you can start putting things in the Fourier domain. You can put filters. When you multiply by a mask in the Fourier domain, you perform a convolution in the real space. The Fourier transform of a convolution product is the product of the Fourier transform. So this operation also stands. For instance, if you put a limiting mask that says that you only allow certain rays within this range of your area, you basically apply a multiplicative mask function that sets the field to 0. This is called this is referred to as an optical transfer function. And what you do here is you multiply in the Fourier domain, which means that you apply a convolution in the real space. Namely, the Fourier transform of this operator will be applied at any point in space, and you basically will have a convolution product with real space. So we have a simulation that does that to simulate, for instance, an aperture limited system. What you can see also is that the system that limits the aperture defines your point-spread function. Your time bandwidth product, for instance, tells you that the extent of a field in the real space here, let's say x, and the extent of the field in the k space here, which will be your Fourier space, are related by this time bandwidth product. Consequence of Fourier analysis properties, if you apply the Parseval inequality to a function and its Fourier transform, you'll end up with this result. What that tells you is that if you have a system with limited aperture size, the size of the smallest feature you can resolve will be greater than a certain fundamental limit. That's basically the resolution limit of an optical system. So we can apply that to our simulations. For instance, here in this demo that you can download, there is a simulation where we use a Fourier transform to simulate a lens. And so, for instance, you start with a certain intensity pattern, and this is what you see in the Fourier domain. So a lot of energy is in the center. This is displayed in log scale, so you can see anything. But then what you can do is you can apply a multiplicative operation by saying, I'm going to put a mask, and you can see the mask here. It's a pinhole that cuts off all the light except right in the center here. When you apply another function that simulates the effect of a lens, a simple Fourier transform, from that data here, you end up with the image right there. If you think about it, you have applied a convolution to this image to get that image. And the convolution is the Fourier transform of this aperture here, which is basically a blurry object. That's the point spread function of your system. You can also simulate the point spread function. You take a point source here, which is not really visible. You transform this point source, you put a mask in the Fourier domain, and you will obtain the point spread function, which you can then propagate step by step. So this is all done with the three function, the one that simulates the lens, the one that simulates propagation. And you can create a visual rendering of what your point spread function looks like in the detector plane, and have, for instance, this very simple simulation of what a point spread function looks like. That so far summarizes what I wanted to say about holography, about wave optics. I'm happy to answer any question at this point, if any of that was not really clear, before we move on to 3D shot. Are there any questions? All right, so all the code has been heavily commented as I was preparing for these talks, so about an hour and a half ago. And all the MATLAB functions are commented. If you have any trouble with them, please send me any feedback, and I'll gladly update the code to make it even easier to read. So there are 3 functions: one to propagate through free space, one to perform a Fourier transform through an FF system, and everything you've seen is a combination of the 2. Actually, there are 2 functions, really. It's even that simple. And you can run lots of simulation. You can simulate, for instance, a dark field microscope by doing filtering, by cutting off the DC term. There's lots of things you can do just with that. So most of wave optics can be done with that. In fact, we'll get back to it later, because you can also do Gauge-Saxton holography with that. All right, so no questions? All right, so moving on. This part is about a technique called 3D shot that I developed as a postdoc. And the idea of this holographic techniques is that we would like to create a device that can activate neurons and satisfy the wish list that we had on the board before. So what we want is a single shot device that can target all the opsin that would be in a neuron, do so simultaneously in multiple neurons at once in 3D, and ideally extremely fast. So how do we get there, and what are the key ingredients in this mixture? So we first start by saying that we need a multiphoton technique. Why is multiphoton microscopy so much of an interesting process? The idea is that in brain tissue, which is, for instance, very well simulated by the suspension of fluorescein, there's lots of autofluorescence, there's a lot of absorption, there's lots of diffuse optics going on. Namely, if you're trying to shoot light at a neuron that is deep in the brain, the photons you're sending in are very likely to never make it to the target, either because they're absorbed or because they are deflected towards another direction by the structure of the tissue itself. 2-photon processes, however, shift the wavelength to the infrared domain. So instead of exciting with, let's say, blue light to get green light, you now excite with half the energy, so double the wavelengths, infrared light, and you count on a multiphoton process to bring the electrons in the excited state and trigger the same fluorescence. Here, what you can see in this 2-photon experiment here is that we have the ability to confine light very, very well. The reason for that is that the statistics of absorption of 2 photons at the same time is proportional to the square of the intensity. While for single photon absorption, the response of the material is very linear. For every photon you send in, the probability of absorption is about the same. And when you go to a multiphoton process, what matters is the square of the intensity. So let's do a bit of physics with the hands now. I have, let's say, a focus beam. So I take a laser beam.
You can erase stuff, man.
Sorry?
You can erase all that.
All right. So I take a laser beam, and let's say it's, widened laser beam. My light is propagating this way. I have my wave coming in, and I use a lens to focus the laser beam into a nice Gaussian beam. The 1-photon process tells me that if I worry about the density of photons, if I put my hand here, I have a certain number of photons hitting my hand at a certain point in time, and as I move here, the photon density increases, the same number of photons arrive, and then if I move further, the photon density decreases again, but the same number of photons hit my hand. So if you have a linear process, the intensity distribution here says that the sum of the intensity is the same. If you have a linear absorption, the number of green photons you're going to trigger in a uniform material is about the same here as it is here. And so as you go in brain tissue, for instance, the wave intensity is going to decrease significantly, and you're going to have an emission of photons that's happening along the way that is not necessarily centered there. When you go to a 2-photon process, what matters now is the square of the intensity. So if you look at the intensity as a function of z, for a 1-photon process, you get that. Now if I look at the square of the intensity and integrate the square of the intensity here, because my field is widened over a larger area, the square of the intensity integrated is actually way less here than it is here. Here, I have a very small area, the intensity, the power density is high, the square of the intensity over this power density is much higher, and therefore if you integrate the square of the intensity in xy as a function of z, you'll get something like that. This confines your excitation. This is why with a linear process you see that, and with a two-photon process you see this confinement. Secondary advantage, because you now have a wavelength that is more in the infrared domain, the ability to go through tissue is actually enhanced. Typically blue light propagates through tissue way less efficiently than red light. You can see that if you take a flashlight behind your hand, that's pretty much tissue, and you can see that red light will go through while blue light will be more blocked. So dual advantages, infrared light and a multi-photon process that changes the absorption statistics to the square of the intensity. So multi-photon methods are very popular for brain imaging, for photostimulation as well. So how have we gone about photostimulation? So this is some of the early work on photostimulation. You can take an imaging system like the one we've seen downstairs and focus a diffraction-limited spot. And by scanning this diffraction-limited spot over the surface of your neuron, you can hope to activate all the opposite. The problem of this technique is that if you scan across a surface point by point, you time gate the activation. And what happens is that you need to integrate the effect of activation across all the opsin to create a strong photocurrent that will eventually depolarize your neuron and, for instance, trigger an action potential. Namely, because you're scanning, the timing of the activation is not extremely precise. So scanning techniques have this advantage of being easy to implement in 3D and rather high resolution, but they don't allow you to scan to create this very brief, strong flux of photocurrent that will precisely time the action potential. In order to address that, holography is one possible pathway, because with holography, you modulate a wave with a special light modulator, and you can literally draw an illumination pattern that covers the whole surface of your neuron. However, because of that drawing that just did here, as you cover a larger area, because the photon flux is still the same across this whole beam that focuses across there, the two-photon process is actually extended, and the number of photons that are received here and there, as you increase the size, for instance, this is a map of the two-photon excitation process, as you increase the size of the covered area, the extent along the z-axis, so I should have flipped this image, is actually growing, which means that if you have, for instance, a neuron that's here, great, the neuron receives plenty of light and the excitation is going to be strong, but if you have a neuron above and below, you're also likely to excite it. So now you have very precise temporal resolution, but you do not have the single neuron resolution you were really attached to. So temporal focusing addresses this type of a problem. So how do we make temporal focusing possible? Well, you take your femtosecond laser, and as we said before, the pulses are very narrow in time, therefore they contain multiple colors. Their bandwidth is really wide. I mean, a couple nanometers, but wide enough. If you break this pulse on a diffraction grating, you will split the pulse into colors, and each of the colors can propagate on a separate path. And this is another 4F system, if you use a 4F system to replicate here the field over there, on each of these paths, the photons are propagating in pulses that are very narrow in color, therefore broadened in time. But as all these multicolor pulses interfere constructively right here, when they all meet at the focal plane, they recreate the pulse that is narrow in time. And by doing so, what you do is you break the pulse into colors, you spread the pulse in time, you reduce the electric field, because the same energy is available across a larger period of time. You reduce the electric field, you reduce the intensity, you reduce the square of the intensity even further, which means that your two-photon excitation diminishes as soon as you leave the diffraction grating. Namely, at the focal plane right here, you are able to excite a very wide area, but very narrow in Z. And if you tune the diffraction grating efficiency, you can basically adjust the depth of this temporal focus and confine the excitation light very narrowly in Z. So how do we turn this into a device that can target multiple neurons at once? Well, we use an SLM. And with an SLM, we shoot at the diffraction grating, and we make, for instance, 2 targets. And each of those targets will be creating 2 images into the optical system targeting different neurons. So you basically draw what you need on the diffraction grating. And you can see here what the issue of this technique is that the temporal focusing happens at the image plane of a diffraction grating, which means anywhere here. But since your brain is three-dimensional, it doesn't happen above or below. So that technique has excellent temporal resolution, excellent spatial resolution, but unfortunately doesn't work in 3D. So what we've done, this is a simple graphic, and we basically said, what can we do the best of both and try to retain the benefits of Fourier holography, and this is an animation, so that's understandable. Retain the benefits of holography and temporal focusing in a technique that combines the two in a way that makes both these possibilities work together for the purpose of photostimulating in the brain. So this is how we go about. We start with something that works well. We say, look, I can make a single temporally focused object. I'm going to call this my point spread function. And if I shoot this object through a lens, I now go to the Fourier domain. And in the Fourier domain, I can put my SLM and modulate the wave in the Fourier domain to try to replicate my object at multiple locations. If you try to do that just like that, this is what you see if you put the IR card on the spatial line modulator, and if you ramp up the power, you'll basically burn your SLM because you have most of your light spread across a line, a horizontal line, which is the spectral frequency line. So naturally, temporal focusing and 3D holography are not compatible. So we had to play with whatever degree of freedom was left to us. And one that we can play with is the phase here. If I add in this location a little perturbing element, for instance, a lens, or there are multiple techniques. You can use a diffuser, you can also use a secondary SLM, or an engineer point spread function a phase object. You can play with the phase in a way that spreads the spectral pattern, or the phase pattern, much more broadly on the SLM. You can distribute your energy way broadly on the SLM. But the SLM still stays in Fourier space, which means that if you apply, for instance, a holographic system, a holographic computation on your SLM, you say, can you, for instance, target those 3 points? And you literally compute a hologram that targets specific points, diffraction limit points. Your system will operate a convolution, which means that if you had a point source here, your hologram would target point sources. But because you have this this temporally focused finite size object, at every point of your hologram, this device will create a copy of the temporally focused object at custom XYZ locations. So to make this device work, all we need to do is compute on our SLM a hologram as if we were trying to target diffraction limit spots at the location we wish to target. And by design, because this is a convolution in the Fourier domain, this object will be replicated at each point. So this technique, as a device, can make objects that are fit and tailored to the size of a neuron soma. That's basically our virtual point spread function. So you can see from the imaging perspective, it's a terrible holographic system. It has a resolution limit that is like 10 times bigger than a typical imaging system. But you can make those types of holograms. You can make custom distributions of points. This is a 2-photon tomographic image, so we reconstruct the 2-photon excitation in 3D. So you can make those types of holograms, and if you have a neuron on each of these targets, you'll be able to very precisely place light in a way that will generate this 2-photon excitation pattern in all those locations. So this is another image. You can make as many targets as you want. You've split the energy that is available in your pulse, so you need very high power laser to make this excitation pattern. But this is what the technology can do. So we did a couple of tests. So for instance, we compared holography and 3D shot. You take a cell, you patch it to measure photocurrents, and as you scan a holographic spot or a temporally focused spot, you can see that you have enhanced confinement in depth. We did another experiment that's a little bit funner. You take 2 spots, so a single hologram with 2 spots separated by a given distance here. You patch a neuron, and you see with holography that you have, this distribution of photocurrent. And if you do the same thing with temporal focusing, you can bring your photocurrent down to 0. If you add to this distribution the nonlinear response, the physiological response of the neuron, and look, for instance, at spike probability, this added nonlinearity creates the same distribution. And what you can do basically with this situation is you can create a hologram that very precisely can activate 2 neurons on top of each other. And if there was a third neuron stuck in between, gives you a situation where you will not be stimulating this neuron. So this would be, for instance, the worst case scenario where in holography, you still have a significant amount of photocurrent, and you'll be more likely to excite the neuron that's in between. Also, keep in mind, the expression of the opsin may vary very wildly from neuron to neuron, so you really want this to be as sharp as possible to ensure that this can be made possible at least as often as possible. So the technique was really designed in a lab that has extensive capabilities, and the team I work with is really focused on all the aspects. So we designed this technique in combination with an opsin that can operate fast. So they developed this opsin where if you test it, for instance, on those light pulses, give you those spikes. So with less than 1 millisecond jitter, so very strong photocurrents and very, very good reproducibility. But basically, every pulse will give you one spike quite reliably. So the idea is that one pulse gives you one action potential with a very strong success rate. So this is the ST Chrome opsin, and this is everything is detailed in this Nature Neuro paper. The lead person was Alan Mardinley on that. So how do we implement this device? So for instance, you take an imaging multiphoton laser. We've seen multiphoton imaging systems, so we've seen about 2 of them today. 3? 2? I don't know, many. But 2-photon imaging with resonant galvo mirrors. You send that into your microscope system, so another 4S system right here, and you can collect your green and red channels, for instance, and use a polarizing beam splitter to merge 2 optical paths. So this is a holographic system, and if you want to have 3D shot, you just put the engineer point spread function here with the diffraction grating and the rotating diffuser. Your object here, your engineer point spread function that's temporally focused, is right here, and you'll be able to create those custom excitation profiles. So basically, these 2 structures are merged on the same optical system, so this starts to be quite extensive of a device, but that gives you the ability to write in 3D with the holographic setup, and to read in 3D if you have a tunable lens here, for instance. And so with that device, we've been able to acquire that type of data. So this is mouse brain. The limiting factor for this technique is really the imaging. So we are only able to image 3 planes at a time and visualize those 3 stacked planes. The processed video that you see, noise aside, I don't know why there's so much noise. It doesn't appear like that on my screen. You have to watch my screen instead, really. It's much more clear than that. This is a compression problem. Sorry about that. But the idea is that the red spots that you see is the DF over F from the calcium data. And the little green arrow that you see flying is the hologram that we're displaying and pointing at individual neurons. So that you can see is that exciting in one plane doesn't trigger significant excitation in the other planes. That's the data aggregated in a way that shows you across multiple iteration, like this line of neurons that we excite in addition to the normal background neural activity. So very, very reliably able to add a specific pattern of activity on top of the background. We can also do ensembles. So for instance, you have here stimulated ensembles of 25 cells and 50 cells. And so this is another data. Still some green background in the back that is not part of the signal. Here the blue color code shows you DF over F, and the arrows shows you ensembles being stimulated. Same sets of depth. And this was basically the experiment that shows read and write capabilities with millisecond precision in custom neural ensemble. So that's pretty much the technique. You can do all these things, which is part of the wish list that we've been talking about. The limiting factor for these devices becomes heat. We are at technological capabilities today where the amount of energy you can put in the brain is on the order of multiple watts. This is literally sticking a soldering iron in the brain. This is very, very large amount of energy. The limiting factor becomes how much heat can your brain tolerate. And so this is really what's becoming the limiting factor. We can make up to 200 targets, but right now the opsins are not sensitive enough to make room for that. So the technology is already ahead of what the opsin can do. And we're looking forward to all this beautiful work in biochemistry trying to make the opsin stronger. So that's all I had to say about 3D shot in itself. I'm happy to answer any question at this point. Feel free to interrupt. I speak a lot. Otherwise, we'll move on to holography. Yep.
Yeah, so I have a question about temporal focusing in general. Can you go back to slide 30, I think?
3?
30.
30.
so in a typical two-photon microscope, right,
Mhm.
the output of the laser would basically be in the back aperture plane, right, of the microscope, and then you would focus that 4 mm beam or whatever down into
Mhm.
to the objective, right? And here you have the diffraction grading basically in the imaging plane, right?
Yeah, so for instance, if you were to, so for instance, the special line modulator here, I'm missing a lens to create the hologram.
Yeah.
But the idea is that you would have this assembly to be right before the tube lens. So for instance, this would be a magnified 3-dimensional or 2-dimensional object that you would then relay to your brain via one tube lens
Yeah.
and the objective to demagnify. So this would be a magnified version of what you would see under the objective,
Got it, yeah, okay. And then
which
the-
is relayed
yeah.
to the diffraction grating. So functionally what you do is you create a virtual image of the diffraction grating in the brain,
Yeah.
and on this diffraction grating you make a custom 2D pattern that you can draw with your SLM with 2D holography. Yep.
Got it.
Maybe a very naive question, but at least in principle, if you had information about the geometry of your diffraction grating, would you be able to create an hologram that is able to perform temporal focusing at 3 different spots? If you know,
Yeah.
in principle.
Yes, so this is actually one of the techniques that have been developed concurrently with 3D Shot, where they use 2 SLMs with the diffraction grating in between the two. And in the first modality that was implemented for that, the first SLM, I forgot if it was the first second, but basically one SLM would split the holograms into multiple sub-holograms and apply a defocusing lens to virtually move a portion of the diffraction grating in the proper, at the proper depth. And then on those diffraction grating, those virtual diffraction grating, display custom pattern.
But with only one, that wouldn't be possible.
You would have to have I would say, a diffraction grating that's like deformable if you want. And that technology is not really there yet.
Gotcha.
More importantly, you would only be able to focus one spot at a certain depth per XY location. So you would not be able to target 2 neurons on top of each other, for instance. Other questions? All right, so moving on. All right, I don't know a better way to do that. All right, so moving on to holography. So how much time do you have, Spencer?
Keep going.
Keep going. All right. So let's talk about holography. So this setup is working, and one of the performance limiting factors is that we would like to be able to target holograms fast and to target neurons fast. So for that, we need to compute those holograms rapidly. So how do we make holograms? Computer-generated holography is a difficult problem. What you do is you start with your coherent laser beam or whatever knowledge you have about the incoming wavefront. You will modulate your wavefront with a special line modulator. It's basically a liquid crystal. So this is an array of liquid crystals that are between 2 electrodes. When you apply a voltage, the liquid crystal will apply a phase shift. So you can control the phase shift on a pixel by pixel basis. When you do so, you basically deform the wavefront, and that deformed wavefront will propagate through an optical system. So for instance, here, a very simple lens, we don't have to be fancy, and we'll create a custom illumination pattern. The goal of computer-generated holography is, assuming you know what you want, the pattern that you like to create, how do you calculate the phase pattern that you should place on the SLM that will best recreate this intensity distribution. And so, because you care about an intensity, which is the square of the electric field, and you have this convolutive propagation mechanism, this becomes a complex, multidimensional problem. You have to decide what value to put on 1,000 by 1,000, typically, pixels. So this is a difficult problem. And the most common and historical methods that have been developed for that, 1972, is called the Gershber-Saxon algorithm. It's an iterative strategy that basically attempts to find a solution just by enforcing boundary constraints. So you start from the image plane. You say, I have an amplitude pattern that I would like to draw. That's my target. I will assume that the phase here is unknown. I'm just going to start randomly with a random phase distribution. That creates a complex field. You go back to the demo that we talked about. If you have a complex field, you can propagate it through the optical system, for instance, through the lens. So you use reverse propagation, and you get a new complex field. the phase of this complex field, because you are the plane of the SLM, is your first guess of what you should be placing on the SLM to create this hologram. The amplitude may not be a match with the illumination that your laser provides on the SLM plane. And so what you're going to do is you're going to say, okay, I'm at the SLM plane. This is what the phase potentially should be, but I know the amplitude is not right. I'm going to enforce this AS, the laser illumination amplitude pattern. For instance, a Gaussian beam that you put on your SLM. So you enforce this, you create a new field, and you propagate this field to the image plane. If you look at the amplitude, you can get an estimate of what your field will look like. And based on this estimate, you may be happy or not about the success of this technique. But what you can do is you can say, okay, my amplitude is wrong, but my phase seems to be getting better. You keep the phase, and again, you enforce the amplitude to be what you really want. And you do that for a bunch of iterations, and hopefully things go well. At the end, you have a mismatch between the amplitude that you wanted, so that pattern, which I think I should have displayed, and the amplitude that you're getting. And what you can see from this, these two graphs, so this is a sample that we're computing in order to really display what's happening. You can measure the difference between the hologram you get and the hologram you want. And you can use multiple metrics. For instance, we use two that are common. The accuracy is the L2 norm. It basically measures the match of distributions, intensity normalized, between 0 and 1. 1 would be like identical holograms, and 0 would be actually, I don't even think you can go to 0. Basically, like it goes towards 1 as an indicator of the match of your hologram. Or you can measure efficacy, which is another measure that says how much light ends up in the targeted area. So, for instance, with this Resection algorithm, we can run the algorithm for an increasing number of loops. And what you can see, so we have about 1,000 samples in this pattern. You can see is that as you increase the number of iterations and the computation time, you get better and better holograms, and it tends to converge to a good resolution level. So that technique seems to work. In fact, it works in most cases. However, there is no proof that it converges. It just happens to work. You don't really know, we don't really have good metrics to identify how many cycles are good enough. All you can do is simulate your hologram and see what you should expect in your optical setup. So this is the most straightforward method. You have all the tools to implement this algorithm. In fact, I think I have a simulation. Yeah, this is an example. So here we have a certain target intensity. So this is what we want to draw. And we have a certain intensity profile. So this is a Gaussian illumination on an SLM. And if you apply this phase pattern between minus pi and pi on the SLM with this amplitude profile, after 10 iterations, you will be able to recreate this image. So the code runs iteration after iteration. You'll be able to see the quality of your hologram go up. And this is the residual error, which is 1 minus the accuracy. And you can see that this converges to a decent hologram and may be satisfactory for your application. So 2016, I started to be interested in three-dimensional holography. And three-dimensional holography is a whole other story. The problem of three-dimensional holography is that we usually ask for the impossible. If you think about it, you have the ability to modulate light coming from a laser with an SLM, and you would like, after propagation through an optical system, to create a three-dimensional illumination pattern. Not that one, but something that looks like that. And here, you basically have a goal which is a three-dimensional object, but the ability to modulate a two-dimensional pattern. So you have a big discrepancy here. And in fact, we've talked about it. This is the Huygens-Fresnel principle, where when you generate a pattern of light into this, so if you place a certain amplitude and a certain phase into D, it entirely determines everything else in the three-dimensional world. So most likely the illumination pattern that you want is not even a solution of an equation of this type. You basically ask for the impossible. And it's very easy to ask for the impossible. In neuroscience, for instance, we would like to make a hologram that activates, I'm going to have to stop with that, that activates these three-dimensional distributed neurons. Namely, you want a lot of photons here, a lot of photons here, a lot of photons here, and no photons anywhere else. Basic principle of wave propagation tells you this is not possible because the amount of photons that are coming through along the optical axis has to be conserved. So for instance, right here, there is no light. The photons that reaches those targets have to come from somewhere. Therefore, this type of illumination is not even possible in the first place. So the problem becomes, what is the best way to make the most likely acceptable hologram that matches the illumination pattern that you want? So that's, we've seen that before. You decide on the 2D phase and intensity if you have the option, and you can create three-dimensional holograms. So this is kind of a little summary of what holography can and cannot do. This is every possible intensity distribution. This is the real world. In it are the subset, it's actually much smaller than it looks, but for space we do that. The subset of holograms, I of xyz, that satisfy Maxwell equations. So that subset is the feasible holograms. Within that area is the subset of feasible holograms that can be rendered with coherent light. Again, the illumination patterns we're trying to create are not illumination patterns like the one you see now going in your eye. They're made with coherent waves from lasers. And in it is another limitation imposed by the fact that we have limited capabilities in our hardware, finite number of pixels, and in our software, imperfect algorithms. So the whole purpose of this talk today is to think about what can we do to improve the software. I have some work being done in my lab on how to make that envelope expand. We can talk about that offline if you want. But basically, when you want to make three-dimensional holograms, you can use some of those algorithms, start from there, go from plane to plane, and then use the Resection techniques. There is a bunch of examples providing also online on the InnovoCGH code. But basically, those techniques can lead to some convergence, and you can have like advanced algorithm or like upgraded version of the algorithm, the Resection algorithm, that render three-dimensional holograms with mild problems, which is that sometimes by going from one plane to another, you tend to erase the work that you've done before, and by the time you're at the other plane, the footprint of what you need to do to generate this illumination pattern is completely erased. So in order to address that, we, in 2016, thought about a way to turn this problem into a more well-defined optimization problem. We say here is my optical system is an operator. For every phase pattern that I play on my SLM, I can compute very clearly by propagating the field the illumination pattern I of xyz that this phase will render. And so if I want to write my holographic problem as an optimization problem, I say, well, this F is my holographic operator. This is my optical system. And what we'd like to do is I want to create an illumination pattern V of xyz. That's my target. And I can say, well, I will put up a cost function that defines how well I'm doing. So I compare V and I. And what I would like to do for holography, I want to find the phase that minimizes the cost between the illumination pattern I want and the illumination pattern that my optical system renders when I apply the specific phase pattern. So this is a highly dimensional, non-convex optimization problem. The one thing you should not be doing about non-convex problems is try to solve it with gradient descent. We did just that. And so what happens when you do that? You will go find a minimum. That minimum may not be the global minimum. And what we observed in practice, and this is kind of like still interesting, is that we end up generally in a solution where the minimum, the local minimum we hit, is not only satisfactory, but generally falls better than what Resection is capable of doing. So this technique is extremely slow, but has been able to generate holograms that are way better than some of the iterative techniques that we can create. So this is more like a worst case scenario example, but this is kind of illustrative of what we can do. We've done some statistical measurements. So this is Resection and the performance. This is our method with gradient descent. And you can see that you basically pay with time. Your hologram computation is way longer. But we're able to make a bump and basically push the envelope of good quality holograms further up.
So you just start with random phases or so to initialize algorithms?
We typically initialize with like basic superposition.
Ah.
You could imagine that, knowing that you have sunk cost in the beginning, you should start your optimization with a few steps of Resection hologram. So there is a best way of cooking this problem. The trade-off actually depends heavily on the size of the hologram. So this is more of an illustrative example where we pick a size and compare the algorithms. As you go to larger holograms, this discrepancy here, this space between the two has very varying sizes. So the two can be compared differently. But there might be a way to further optimize the way this initialization process starts. Yes?
This is 2D or 3D that you're
This is 2D. This example is 2D. This is just for time quality comparison.
And the earthquake sections you initialize is just 0 phase, right?
0 or random. You can also choose like what works best. All right. So moving on. This was the second technique that we've been working on. Basically, upgrading from the historical and most popular way to make holograms, this technique gives you extra quality, but at the expense of time. So if you want to make holograms that are very photon efficient, or that best render the very, very precise scene, if you really want to make best use of your laser light, you may be interested in those techniques and compute holograms that give you the maximal photon efficiency possible, knowing that you're going to be wasting a lot of those photons in the brain in heat. So, but we're interested in another category of problem, which is what you can see here, this envelope here, better holograms is going up, faster holograms is going left. We basically would like to push the envelope somewhere that way. More importantly, we were very interested in holograms that can be computed on the time scale of milliseconds. The action potential is a millisecond. Talking to the brain, establishing a communication pathway, a conversation, if you wish, should be done on this time scale. If we're having a conversation and I take an hour to respond to your question, you will be gone. The same thing happens in the brain, where if you start implementing a pattern of activity in the brain and the brain is now in a different state, that communication may not affect the brain as you intended. So we're interested in holograms that are on this time scale. And because the holography is a non-convex problem, if you want to compute non-convex operations really fast, so this is an illustration to say, we're interested in like generating holograms that can activate those patterns. So this is the previous video. It doesn't work. No, it does work. No, it doesn't work. This is a previous video I showed you about patterns in neural activity. Or for more financially interesting operations, like for instance, rendering a three-dimensional object in a VR headset when, for instance, your head is moving. That's the kind of algorithm that we're interested in. And so deep learning is really good of a product to perform this operation. So deep learning with, for instance, a convolutional neural network takes an input and in fixed time will process that input through a neural network and give you an output. Deep learning is really good at computing these nonlinear operations, for instance, holography. So that approach has been tested. There's a paper right here that started doing that in 2018 with a technique called supervised training. So the idea is that you take a bunch of random SLM phases, you simulate the propagation of a wave with this phase, and that gives you a bunch of corresponding intensity patterns. And if you take the pair phase and intensity patterns, you basically have pairs of input and outputs, and you can train your model to perform this operation. That's supervised training. The problem of this approach is that this is the number of holograms that you can make with 8-bit on an 128 by 128 grid, is that by picking random phases, you're going to pick random intensity distributions that may not look anywhere near what you're going to do with your network once it's trained. We're looking at holograms that look like this. The odds of picking holograms that are natural images or scenes that depict what we're trying to do are actually quite low. This is this little subset here of like holograms that we like to do, including cat pictures, because we all love cat pictures. Now, the approach that we developed for that, and this is work that's been done, is to use unsupervised learning. So instead of just looking at this system, we can take the output and simulate the propagation to reconstruct what the hologram should look like. This is differentiable. And so what you can do is you can take a target amplitude and say that the pair of data sets that you need is this target amplitude and the exact copy of this target amplitude. This is what you want. So for training purposes, you can take the target and feed the two together to train the neural network. This is now unsupervised learning. You can also train the network with a custom loss function that is tailored to what you really care in the training purpose and end up training your neural network. So that and a few more tricks that we've been playing that are not disclosed yet but are being written as we speak allows you to train your model with two interesting features. You can specify what data set you want for training. You can specify what cost function you would like to use. And these two are relevant to what we're doing in neuroscience. We have data sets that we know of. We know where they're going to try to shoot at neurons. We have loss functions that are representative of what we're trying to achieve biologically. We know we're trying to pass a certain threshold of light to trigger an action potential. So these two are relevant, and the machine learning is actually really good at allowing you to have this flexibility in your computation. So just to give you a couple results, this is the computation time. So our technique can do computation in about 2.6 milliseconds. That places us right here. So we push the envelope. Our holograms, as you can see, they're not better than what these slow techniques can do. But for the same amount of time, they're way better. And so they basically satisfy and help a niche market in which, good is good enough as long as it's done within a certain amount of time. So this is early results. We actually have better results now. But basically, this is what this type of algorithm is good at. So this is the historical algorithm. This is one way to do research, to try to make better algorithms. This is another way to do research, is to try to make faster algorithms. Moving on, this is the final part of this talk. So am I doing still well on time?
Yeah.
All right, wonderful. So moving on, is I'd like to get this bundle idea into your mind, which is that if we have flexibility in how we compute hologram, we should use it for the greater good. So looking back at what we can do with this optimization technique, NovoCGH, we can pick a custom cost function that represents what we're trying to achieve. With these deep learning methods, we can take a custom training data set and a custom loss function. We can use those to refine our ability to make holograms. So for instance, an example is if you optimize here by saying that your cost function should value not the output intensity, but the output 2 photon excitation. You just turn the cost function to optimize not for the intensity, but for the square of intensity. And you can make holograms that enhance the confinement along the z-axis by specifically targeting that. You're trading off some of the uniformity of the image. This is not really a blob. This becomes more of like a speckled disk. But for that, you get enhanced confinement along the z-axis. This hologram looks uglier than this hologram. So if you give that top image to an imaging specialist, they'd be like, I prefer this. But if you give this top image and bottom images to a neuroscientist, they will prefer this more confined excitation spot. So by tailoring the cost function, you can do better biology. Another example is that we know about distributions of neurons. We can take a nice slow z-stack with our fancy 2-photon microscope, identify the locations of all the neurons, and know which ones have opsin. Now we have a problem where we say, we would like to activate these N neurons. That's not exactly what we're trying to do. What we're trying to do is we're trying to activate most of these N neurons in a context of a distribution of neurons that also have the opsin that we specifically do not want to activate. So you can refine your cost function in order to say, I'm going to not only put a benefit cost at shooting at the red target, for instance, I'm going to put a hefty penalty for any light that hits the blue targets. If you do simple iterative algorithms, or if you don't refine your cost function, you can make holograms that look like this, that visually render the best approximation of the red target. But if you're willing to put the biological cost function in there, you create this very ugly hologram in which your algorithm basically attempts to shoot at the neurons by moving light along lines where the path is clear. Basically, for any photon that hits neither a red or blue target, there is no cost. So you can basically relax your constraints and compute holograms that may be better at achieving the task that you're looking for than holograms that try to match intensity patterns. So this is another way to make better holograms, is to relax the cost function by integrating some of the biology that we know about, some of the nonlinearity we know about. Yes, please.
So how long does it take to train that network, this unsupervised learning? Because you have to do it for every frame, right?
Yes, and well, you have to train for categories of frames. That is that you don't need to train for every frame you're going to make. You need to train for a bunch of frames that are diverse enough that it will help your algorithm converge, and stable enough that a new frame can be generated quite correctly. So I have a couple examples, for instance, that illustrate this capability. So for instance, that's basically so. And that's part of this next slide. So this is showing you, for instance, tailoring the cost function to optimize for a specific biological goal or specific photonic response. Here with machine learning, what we've done is a very simple optimization where we trained on specific data sets. So we take a bunch of points, like subsets of images that contains pixels, images that contains lines, squares, or disks. And we trained the same model on each of these data sets. We had 4 trained models, and then we compared those models with the same data sets. We basically run the same type of data sets, and we basically measure the capability of this model. And what you can see, the diagonal shows you, like, if you train a model on pixels and try to make pixels, it'll perform well. If you try to train a model on squares and try to make squares, it'll perform well. Same for disk. And if you look at the statistical data across multiple iterations through that type of data sets, you can see here that this approach, and this is very preliminary data, I would not, publish that data set as is. The idea is that the training can be refined to specific subsets of holograms. That means that if you know anything about the scene that you're going to try to illuminate, by training your neural network offline on data sets that are representative of this scene, you'll be able to generate patterns that are even better. The idea is that making holograms is difficult, and we know that our computation capability is limited. Even with the largest CNN, you're not going to be able to make a beautiful hologram. The question is, how do you use and harvest all the computational capability you have at the moment to get the hologram to be as good as possible within the computational time frame that you have available to you? And so this is an example that says, well, if you want to make your holograms better and gain a little bit more quality, one way to do it is to optimize the cost function. The other way to do it is to train on data sets that you know are representative of what you're trying to achieve in the end. So on that, conclusion is that we work on new instrumentation. Yes, please.
So one question, why are you surprised about this? So why is that surprise that when you...
No, it's not surprise, it's illustrative.
Okay.
It's one aspect that we should be leveraging in training those models. Like once you have a method to make holograms, the question becomes, how do I train it for that specific application? This is illustrative of capabilities. To say, that's not something that you can do with the optimization technique NovoCGH, but that's something that becomes accessible and should be valued as a way to enhance computational capability. The selection of the training data set does not affect your computation time in the end. So you might as well train on the most representative data set with the best cost function. That's what the point I was trying to get across. So conclusion about all that work is that I really want to push for techniques that move away from imaging systems. The holograms we're making are not beautiful holograms, but they do better in neuroscience applications. The optical systems we're developing are not really good at shaping images, but they're good at placing the right amount of light with the right size of excitation in custom locations. So when we're willing to trade off and go away from traditional image rendering systems, there is room available that gives us capabilities that traditional imaging systems do not have. And this is accessible with new optical technology and with new algorithms that are really tailored with the final goal in mind and with an interdisciplinary approach. You can see sometimes techniques coming out that are really good at doing one thing, but end up having limited neuroscience applications because the needs of the neuroscientist community may not be exactly exclusively around this set of constraints that one technology solves, but broader. What we're trying to do is really take a set of constraints that are imposed by the neuroscience community and try to get the best technique out there that satisfies equally all those constraints or with the right balance between all those constraints. And I hope I've convinced you of those techniques. Moving away from imaging pays off in the algorithms, in the holographic system. So this is the work that's been done. The grad student who's been developing the machine learning technique is Hossein Aposh. He's been working in close collaboration with an undergrad at UNC, Matthew, who's also a machine learning guru. Matthew just got a poster prize at Duke for that, so we went to Duke and we got something. And this is the rest of the lab right now with 2 grad students and a postdoc. And I come here for ads, so this is a conference I organize. In 2021, we'll be in Boston. And if you want your name here, please let me know. Thank you very much. Questions?
Yeah, I think you mentioned this, you know, a lot of the technologies that we use for this spatial light modulators are phase only, right? If you want a high pixel count. And that's okay because phase gives you a lot of the information that you need. That the amplitude is, if you had to pick one, you'd pick the phase because that would be most what you need to reconstruct something in holography. What's your view on the technology for these spatial light modulators? What do you think? There's a lot of headroom for further exploration. Do you think we can get much higher pixel counts? Do you think we can get much higher speeds? Or are we topping out on some of those?
So, well, two things. About the phase carrying more information is actually a really nifty simulation you can do, again with that demo set. You take some picture of a person A that defines an amplitude pattern. You take a picture of person B and you use that as a phase pattern. You create a complex field. The amplitude is person A, the phase is person B. And you do the other one, B and A. You Fourier transform those. And in the Fourier domain, you swap the phase. And you back Fourier transform and you see what you get to see. And you'll see what carries information, and it's the phase. That's a really, really critical point. This is why the SLMs is really a fundamental element in optics. The other element that is relevant to us is that when you modulate phase, you keep your photons. Modulating intensity is typically done by controlled absorption, and you don't necessarily reshape your amplitude, but you rather lose your amplitude in the process. So although we would get better holograms if we had the ability to modulate phase and amplitude, therefore covering every possible hologram according to the Huygens-Fresnel, the holograms that we cover with phase are already covering most of that space and also preserve the photon count, so give us more ability to create custom illumination patterns. And then in terms of technology, there are multiple things that are being done. There is one of them is stability. The same pixel is typically driven by a lookup table of voltage to phase. As we go towards better SLMs, when you're on a wide printed array of liquid crystal on the SLM, the thickness may vary, the manufacturing process may vary, and the lookup table in theory should be different for every pixel. The most advanced SLMs, they have lookup table by clusters that allow you to rectify for some of the manufacturing defects when you're on the edge versus the center of the SLM, or to rectify for some of the holographic defects where the type of light you send to the edge is different than the type you send to the center. The main, I think, where the money is in SLM technology is photon efficiency, reflectivity, diffraction efficiency, the ability to steer light and not send light back to the zero order, and speed. And for that, there is the technique that has been pioneered by, I'm going to butcher a name. I'm sorry, the name is a genius faculty in Switzerland, or sorry, in Austria maybe, somewhere in Europe, that developed the Overdrive technique for SLMs. The idea is that when you want to set your nematic crystal to a certain phase pattern, so let's see. You have an SLM that's basically a pair of electrodes where you apply voltage and in between a liquid crystal. When you apply the voltage, the molecules align in a specific direction and the amount of voltage steers a certain amount of alignment. But when you apply a step function, as a function of time, the phase that you will get ramps up like that, exponential decay, for instance. The idea is that you are only able to use your SLM once you're there. In fact, there is a time, so really you're only able to use your SLM when you're there. That time is on the order of hundreds of milliseconds or milliseconds. In order to go faster, there's a technique that involves playing with the driver, knowing the elasticity and the properties of the crystal, apply voltage that is bigger first to shoot this way. And if you calibrate things well, you basically clamp the voltage, so you basically have a nonlinear pump, and then you hold the crystal in the right location. That technique is computationally costly. It's also electronically difficult, and it requires strong voltage that might damage the crystal in the long term and induce unnecessary heat. But this is where the money is, to accelerate the process of accelerating the SLMs. And then the last thing that we sometimes forget is that SLMs on a pixel by pixel basis have noise. And that noise builds up to fluctuations that affect the phase pattern you're trying to render and affect the quality of your hologram by superposing basically an overall white noise around it. So all these things have to be addressed. Right now the money is really in the speed. Like you pay twice as much for a hologram that goes almost twice as fast. But every other axis is something that can be improved. And it's all about building better electronic drivers, stabilizing the fabrication protocol for liquid crystal, and then, of course, designing new liquid crystals that have faster response times.
So since sometimes we get it, particularly with photostimulation, you get into power limited regimes, what are some common efficiencies that you get out of your system, diffraction efficiencies that you get out of your SLMs?
Diffraction efficiency of the SLM is whatever the manufacturer gives you. So it's like between 80 and 95%, depending on how much money you spend. When you get to faster SLMs or SLM with smaller pixels, that can go down. Also older technology that's typically not as good. The total power efficiency is also relevant. Like from the laser source that you have to the objective, you typically lose a factor 10. That's pretty significant. Right now, the laser cutting industry is driving the laser technology, so we have all the power we want. You're really limited by the brain tissue at this point. So if we had to think about improvements for the neuroscience work in optogenetics, better option is where the money is, because everything else has already been somehow covered. In fact, there are two techniques that are in use to accelerate SLMs. One has been developed by the lab of Diceros at Stanford that uses two custom designed SLMs that operate already at 500 Hertz. So pour money at the problem, you get an extra 50% speed. But then the technique is really crafty, where they use a Optical cell to shift the power from one side to the other very quickly at 500 Hertz, while each SLMs update their frames with a quarter pi phase shift, allowing you to not illuminate the SLM as the new frame is being put on while the dwell time is happening, and then only place the light on the SLM when the SLM is ready to do that. So this is a way that's kind of technologically costly to solve the problem. You can get up to 1000 Hertz. Another technique that I heard of being developed by the lab of Valentina Emiliani at Paris involves playing with the rolling shutter of the SLM and with a galvo mirror shoot the beam at the top part of the SLM to use only a certain sub-portion of the pixels and follow the rolling shutter by illuminating only the portion of the SLM that was last updated to get a sub-window, so you pay with resolution, but you're able to enhance virtually the quality of your holograms. So all those are engineering techniques that can be applied to kind of like go around the fundamental problem of SLM, which is their slow pneumatic response.
I was just saying, so you talked about how the problem is that there's heat in the brain when you do these 3D shot stuff. So what does that mean, like experimentally? How long can you run an experiment before to worry about drawing stuff?
So with the options that were available as of 2018, we were able to excite 50 neurons every 2 milliseconds without significant or measurable brain damage across like 20 minutes of experiments. That's pretty much what the limiting factor was. Yep.
Can you define brain damage?
So brain damage, so I'm no neuroscientist, but brain damage was assessed by immunostaining, if I recall, where you look at the health of the neurons before and after exposure.
Can you define health?
I don't know exactly. You would have to contact. You would have to contact.
Heat shock protein or something?
I think heat shock protein. Yeah, I think that was the technique. You would have to contact Alan Mardingley or Ian Oldenburg if the info you want is not in the supplement of the paper. It's figure Z1 or Z15 in the paper. We had to do those experiments. I don't understand those experiments myself. I just heard we had to do them. This was like far away from where I stand. Ask Alan or Ian.
Okay.
They'll know that.
Yeah.
Sorry about that.
Yeah.
These SLMs are all transmission.
No, they're reflective SLMs. So sometimes I display them as transmissive elements for clarity on the object. They're typically liquid crystal on SLM, liquid crystal on silicon. So it's a silicon base that's reflective. There's a liquid crystal that's deposited on it, and typically an anti-reflection coating on top. Most SLM technology that has high diffraction efficiency is typically and speed is typically reflective. I think the benefits of it is that you only need one conductive layer that's transparent. So typically I think it's ITO. I don't know exactly. But it's difficult to make conductive and transparent materials. So like transmissive is typically harder to make and therefore less efficient. But you can do the same thing with both. In fact, even if you, the main technique we employ is we shoot the light at the SLM at a shallow angle, and we get the beam that comes back. There is a way to play with polarization and quarter wave plates that allows you to be straight on the SLM. You basically hit the SLM with one polarization, pass through twice through the same quarter wave plate, and rotate the polarization, allowing you to collect the opposite polarization on the beam splitter. So you shoot the light through the beam splitter, it's transmissive. By the time it comes back to you, it's reflected. So this is a simple trick that can be used to like go around that problem. Yeah.
So what's the typical laser power do you use, and do you also have dispersion compensation? Or
Excellent question. So typical laser power, I think the techniques that were published were used with a 18 watt femtosecond laser, typically around megahertz capabilities. This is all in the paper. We also had a 40 watt 1040 nanometer, again 1 or 2 megahertz depending on the settings. You want extremely large pulse energy because again you're going to divide your energy across multiple targets. And the pulse are on the order of 200, 300 femtoseconds. Now, do we employ pulse dispersion compensation? Some of the lasers we had a chirper built in, so we did use that, and with the same approach of measuring the maximal fluorescence, or with an autocorrelator. And but what we observed is we used lens doublets, and we didn't go through as much glass as you have to when you go through those like super fancy microscope devices. So pulse compensation was not so much of an issue. The other thing that we suspect is because we're doing temporal focusing and literally building a pulse compressor, the diffraction grating in the lens is a pulse compressor. What happens is when pulse compression is actually a little bit off, you basically have a defocus that happens between the plane where you recreate all the beams merging together and the plane where all the pulse interfere constructively. So you might be off by a micron or two up and down when you recreate those. So you can geometrically compensate for that. We didn't notice anything that was worth fixing in a point spread function. But that would be a case, one of the rare cases where pulse compression might actually not be so much of an issue.
Great, thank you so much.